A couple classes ago, we talked about what a reptile was, and a tessellation of plane is sort of similar. It's the idea of taking a figure and covering the entire plane with the exact same figure without any empty spaces. So, like for example, if you were to use a square, let me grab my pointer here, to tessellate the plane, it'd be very simple because you would just copy paste square after square, creating a congruent figure where each of the points of the square were connected to one another. And you could imagine this continuing forever in any direction. But we often graph like maybe 5 to 10 or whatever of those figures to sort of help visualize, that this will continue under that idea. And now with certain types of polygons, it's actually possible to tessellate in different ways. Like for example, with squares, you could connect them all in a perpendicular way, or you could kind of offset them where the tessellation creates this other sort of pattern. And in this case, sometimes you would refer to this as tiling, creating tiles of different shapes. And these are some common tiling patterns. But you can also tessellate the plane with other shapes like rectangles, triangles, pentagons, whatever. It depends on what a lot of the properties of those figures, and that's what I wanted to talk a little bit about in this video. Like what are some of the different types of tessellations? Like here we can see an equilateral triangle is also very easy to tessellate the plane with, as is a regular hexagon, because those shapes naturally fit together. And actually, what's interesting to know is these are the only three figures that you can perfectly tessellate the plane with because of the divisibility based on 360. Or like if you look at the interior angles of each of those shapes, the ones that are divisible, 360 divides those numbers, or like 120 divides 360, or we'd say 360 is divisible by 120. So I'm trying to say this properly. But I think you know what I mean. It's because if you look at where the shapes connect together, like say for example with these hexagons, obviously any complete circle must be 360 degrees. And if we look at the interior angles, well, those are each 120. So naturally those three add up to 360. And that's one of the keys behind tessellating the plane, is thinking about how the angles fit together. Or like with an equilateral triangle, all of those angles are 60, so 6 of them naturally connect together to add up to 360. Or with a square or rectangle, they all add up to 90. 90 times 4 is 360. So those, when it comes to regular polygons, specifically those 3 regular polygons tessellate the plane, but none of the other ones will, because none of those divide 360. But when dealing with non-regular shapes, they can tessellate the plane in many, 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 many different ways. And a few examples that I thought were interesting from our text show a few interesting shapes of pentagons and how those tessellate the plane. And they talk a little bit about a non-mathematician who saw an article about this, and she discovered more types of shapes. About with specifically the pentagon, using a lot of the properties behind tessellations. And actually one unsolved mathematical problem that still exists is we don't really know, is there some sort of algebraic formula that will tell how many different ways can a polygon tessellate the plane? Like say for example a pentagon. Are there 10 different ways, 20 different ways? Is there a finite number of ways to tessellate the plane with these shapes? We don't really know. But like quite a few different ways have been discovered, especially when it comes to larger and larger shapes. There's actually way more possibilities. And also, if you're wondering, well, how do I see the pattern behind here? This is another thing that can help you visualize tessellating the plane. And my recommendation would be to kind of look for a repeating pattern that you can see in a figure. Like in this particular, the shapes will connect all together in a way that provides a repetition. Like if you're looking at the orientation of some of those pentagons, they seem to be all helter-skelter, but there will be some form of pattern. And like if you look at this pattern further, notice that you can find a larger group which is repeated upon itself. And that kind of helps you see how it's tessellating the plane. And the last thing is actually, when it comes to quadrilaterals specifically, any quadrilateral will tessellate the plane. It doesn't actually have to be involve right angles. Like, it doesn't have to be square, or it doesn't have to be a rectangle. Because if you look at this particular image, let's say we're dealing with a quadrilateral where all the sides are different and all the angles are different. A, B, C, D representing those particular sides. If you kind of notice how it's been constructed, if you put all 4 of the angles of the quadrilateral together, those will have to add up to 360. And this will give you a pattern of repetition where basically you can continue stacking the quadrilaterals on top of each other. And it actually helps to think of these as undergoing a rotation. Like, notice how one of them has been kind of copied below down here, and the other one has been well, you can tell it's a rotation by 180 degrees in either case, to find the other particular points. But one of the strategies that our book says to do is if you take each midpoint and rotate by 180, that would give you this figure over here, but upside down. Notice it's not reflected, but it is rotated. And we'll practice trying to create a tessellation in a second. And again, if you were trying to do a construction, you could perform a rotation to do this. Just rotate each of the opposing vertices, like here, rotated about point S by 180. By, again, just drawing a straight line through it, taking your compass and rotating it like that. Same with this point C, draw a straight line from C through the midpoint. Again, you could find the midpoint by a bisector method that we talked about a couple weeks ago. But anyways, then you could rotate C like that. And again, you could go through a more tedious form of construction, which if we were doing this in class, we would do this more accurately. But since we're doing this lecture online, it's a little bit harder. But you can try it if you want to when you're doing this in your own notes. And last but not least, we're not going to do an example of this, but actually you can actually take certain types of figures and perform make them more convoluted into a tessellation. Like, for example, with a rectangle, if you actually cut out part of a rectangle and kind of paste it on the other side, notice that this would form a nice tessellation, because if I were to just, this part is exactly congruent to this part. So if I take a copy of this and, translate it over here, it'd be exactly the same shape, and that would naturally tessellate the plane. So this is when it comes to something like snowflaking or quilting, these sorts of ideas are very, very helpful for creating really cool types of imaging. And you can see one application of geometry, in this particular subject. But let's look at an example. Let's try to take this quadrilateral and tessellate the plane with it. And again, if we were in class, we'd do this a little bit more precisely, but we will just do our best to use my iPad to sketch it out. But again, basically what I want to make sure to do is replicate the same figure over here to begin with, because all 4 of the angles, like if I call this A, let's go ahead and label this A, B, C, and D. Each one of those all 4 of those would have to add up in the center. So really I'd want to make sure A, B, C, D are all here. But basically C, I could paste right over like this. So I'd just kind of copy that edge and copy that edge. Just pretend this is precise, which it is not. And that would give me, again, kind of like D, C prime. And then I would copy this edge here. And notice that, again, I could keep, if I was trying to figure out what angle to do this, I could use the parallel technique to create a parallel line here, and then use a compass to create a line of equal measure there. But basically, I'd have something that looks kind of like this. And that would create my first image, assuming I did this better. And then in terms of the 2 over here, we want to think about rotating this image like that, about 180 degrees, about the midpoint of each of the respective sides. So essentially, this line would be replicated. This line would be reflected and would be over here. So essentially, I know that this would have to be parallel to that line if I was trying to do it that way. And really, there's only one last side that I need, which would be this side right there. And that would be kind of the combination of CD. Again, this is not very accurate because I am not using any rulers or compass, but use your imagination, pretend I am doing this better than I am. And then with the last side, it would look something like this. What am I doing wrong here? So yeah, if I was imagining taking this edge and rotating it, then AD would be the same side, BC would be over here, and I would need AB, CD should be right there. So yeah, the issue here is that this isn't quite long enough. And so again, trying to do a tessellation as I am, probably just shouldn't do it. And we'll leave it at that. I'll let you try it on your own. And if you're getting stuck with something, we can talk about this next week when we're back in live class. I'm also going to record a couple videos on chapter 14. Let's get started on that this week, and next week we will continue. But chapter 14 is all about measure, things like area, volume, and I want to cover a lot of those formulas and focus on a lot of the logic behind things like the Pythagorean theorem, or what's the volume of a sphere, so on and so forth.